Okay, so we did this at the end of class. I would just zoom through it really fast to just start get our bearings here. How many people? So I asked you to bring this handout again today. So if you didn't bring a copy, or you started on your written homework and you don't want to keep writing on it, how many people need a new copy? So could one of the TAs help me out with that? I just have some. So hopefully you just brought yours from Friday. Okay. So just keep your hand up until you get one. All right. So I'm gonna go through it. Just the same thing we did at the end of class. So we're talking about that. This is a rate of change function, right? So y values give us rate of change. And so then we're focused on a moment at 0.7. Okay, we're focused on a moment at 0.7. It's a really small time interval. And we said if we wanted to represent that rate of change at that moment, it would be a constant rate of change. So on a rate of change graph, that would be a horizontal line, right? So a horizontal line such that that rate is 9.68 through that whole moment. So in this moment, we assume a constant rate of 9.68 meters cubed per day. That's that horizontal line on the rate graph, right? So now in that moment, we want to build a little bit of accumulation at that rate. So it told us that at 0.7, the current amount of accumulation was 13.15. And now it's asking for f of 0.7013, which is right here. Which is way at the bottom of the screen there. So 0.0713 is right along this line here. A little shaky today. Okay. Something like that. Okay. So along that 0.7013. And so if we want to find the final amount of accumulation of 0.7013, it starts with what? It starts with a change in x, right? So what is the change in x that we're talking about? Okay, the change in x is final value of x minus initial. So 0.7013. Thank you. Final value of x minus initial value of x was 0.7, giving us a change in x of 0.0013. So we're going to let x change by 0.0013. And as x changes, what happens to the amount of oil in the ocean? If x changes, if time changes a little bit, then the amount of oil in the ocean does what? Goes up. How much does it go up? It goes up by some amount which we represent as dy. And and we know that because we are at a constant rate of change, it's going to be 9.68 times, so m dx, or 9.68 times 0.0013. And how much did we get for that? For that dy? 0.01 what? 2? 26? So something like that. So when time goes by a little bit, 0.0013 days, the amount of oil goes up. And if it's going up at a constant rate, we can use our constant rate, 9.68 times the change in x. And so then we have our last important principle, which is that y final, or v final. So y final equals y initial plus change in y. And so v final is our v of 0.7013. And that equals, what's our v initial? That's our v of 0.7 plus our dy, which we got by m dx. So that the y value, or the amount of accumulated oil now at little time later, is the amount of accumulated oil to start with, plus how much that changed, m dx. So we've got all that stuff, so I'll rewrite that up here now. So V of 0.7013 is going to be V of 0.7, which we were given, the initial amount, 13.15, plus our change, which we calculated here, the 9.68 times dx, and we got 0.126. 0.126? Is there a 0 in there? Okay, so thank you. And so we got 13.1626 meters cubed. Is that meters cubed or meters cubed per day? This is, now we're finding accumulated amount. So over here, we're at meters cubed, okay? And so that was that final amount right there. The y value right here is that 13.1626, which we got from this very important principle. Final value of an amount is the initial value plus its change. And then we applied that to say, what if we want any, so as the time changed, really, we had a whole bunch of correspondence points in this moment, right? As time changes through this moment, we have an unlimited number of correspondence points. What if we want to write a general rule for any one of those correspondence points in this moment? We could call it then, we could just pick one of these to represent all of them, right? And it would be xy. And so now, what would the change in x from our starting x to x be? So now we have dx equals x minus the starting value of time. There's our dx now. dy is our constant rate, m times dx, so 9.68 times x minus 0.7. And then final value of y equals initial value of y, 13.15, plus the change in y. And so what does this do? Now so finding this value was good, but this is really good. Why? Because it gives us every amount of accumulated oil within this moment. For any value of x number of days, we get the accumulated amount of oil in this moment at 0.7 days. Okay, also I'll recap. Okay? Anybody have a question? Yeah, please. Because remember when we started with our accumulate, we're looking at accumulation functions like a week or two ago. And what did we do? We zoomed in far enough until we saw what? Yes, until it appeared linear. And then we say we have essentially a rate change in a moment. So we're making the assumption that in this volume graph, if we zoomed into that amount of precision, from 0.697 to 0.703, this would look linear. Okay? Although it's not quite. And I'm exaggerating the not quite with the red. So, does that make sense? Yeah. So it's the way that I have the scale, that fact that rate is still looking like it's changing is kind of exaggerated. But we're zoomed in far enough that we know that this graph would appear linear, so we can assume constant rate. Good question. Very good question. Okay. So let's just recap big picture here. Let's recap big picture. So what are we doing right now? Left graph, rate of change of oil entering the ocean. This isn't on your handout. Don't worry, this isn't on your handout. Rate of change of oil entering the ocean and accumulated volume of oil leaked. Okay? So what journey are we on? You know how fast something is changing. In this case, the rate of change of oil entering the ocean. And what do we want to determine how much of it we have. This is the journey we're on right now in the next couple weeks, or 3. Okay? So what is that about? So the key to this is constant rate of change. We're using these key principles of constant rate of change to do this. So given m, right? Given m, what can we say? We can say that dV equals m dt, right? That's constant rate of change. So we can get a little change in oil amount is equal to m times the change in time. And then from that, we can use that then and say we got a final value of oil is equal to initial plus the change. So how do those equations then match this journey? How do these equations that you're looking at down here reflect this thing that we're on? Well, yeah, thank you. Okay, so how do these equations reflect that? Well, we're given the constant rate, right? So we're given a rate of change function from which we can get a constant rate right here. And from the constant rate, what can we get? We can get a little bit of accumulation. So given rate, we want to know accumulation. So given rate, it gives us a little bit of accumulation, and then in addition, it gives us a net or total accumulation by using this V final as V initial. So given M, we can find dV and V final, and that's what we want. We want to know how much dV, how much change, or how much do we have in the end. See that? So these constant rate of change equations, they embody exactly the thing that we want, right? So we know how fast it's changing, that's M. We can find dV and V final, how much of it we have. Get it? Okay. But there's a big problem with what we did on is there a question? Are you good? Okay. All right, so this previous example that I just worked through, there's a big problem with it. What is the big problem with this thing I just did? Right? We did all this work and we got what? We got it. We got the equation for the amount of accumulation. But what is the big disadvantage here? Yeah. Right, and is that a lot of time or a little time? Okay, so what percent of this whole from 0 to 2 days was that moment? Just a minuscule fraction, right? And so if we wanted to build it that way, we'd be here this semester and next semester, right? Doing these moments one at a time like that. Okay? So we need a kind of we've got the idea, right? So this was a great example to see the idea of where we're going, but we need to kind of take a different approach to this if we're going to make some more progress at uncovering that whole function, not just a moment of it, not just a minuscule fraction of it. Make sense? So now we got to take a new kind of approach on this. All right, so here's what we're going to do. We're going to start with that again. And what I want you to do is I want you to you're going to highlight, so now this is on your handout. I want you to highlight points at every 0.4 days. Highlight correspondence points for every 0.4 days, starting at 0. And then for each one of those points, I want you to write the correspondence point as an exact values or representations of exact values. And then I want you to write approximated amounts. So let's do the first one together here. So how would we write that one? Exactly. I want to represent that correspondence point exactly. Robert.
0, r sub v of 0.
He said 0, r sub v of 0. Does that represent that correspondence point with exact values? Yes, right. And then your next step up for each of these points is then what is our v of 0? About, estimate. What is our v of 0? So we look at that and we say, what is that about? I agree. We want to do whole numbers, or do to the nearest whole number to make it easy. So about 28 meters cubed per day. And where do you see that value? How do you know that? You zoom in and do dy over dx? Where do you look? Y-axis. It's a rate of change function. So if you want that particular rate of change or an estimate of it, you cruise over the y-axis and you pick off that value. rate of change functions, their dependent variable is the rate of change. So I want you to do this same thing for every 0.4 days. So you're going to 0.4, 0.8, 1.2, 1.6, and 2. So both exact and approximate rate of change. Both exact coordinates and then approximate rate of change. Okay, where's Benjamin Leigel? Benjamin. Did you get the next point? Tell me. Okay. All right, so you said 0.4, RV of 0.4, approximate value 17. That's what I got to. Agree with that? Make sense? Okay, where's Nolan? Tell me, Nolan, did you get the next point? Yep. I'm seeing 8. Yeah, I'm seeing 8. Yep. 0.8, RV of 0.8. I'm saying that's approximately 8, that rate. Okay, Megan Allen. Where's Megan? Tell me. Next one. Uh-huh. I got 3. The next one's a little higher. I chose 4 for the next one. So, yeah, 3 or 4. If you put 4, that's perfectly legit. I'm putting 3. Okay, next one is 1.6, RV of 1.6. I'm seeing that as approximately 4, and that's where I stop. So if you did 2, that's fine, but I'm going to stop here at 1.6. Okay, make sense? Okay, now here's what I want you to do. I want you to look at that first interval of from 0 to 0.4, and I want you to illustrate a constant rate of change in that interval equal to RV of 0. So illustrate in that first interval from 0 to 0.4 a constant rate of change just to 0.4 at the same value as R of V of 0, or approximately 28. Can you do that? Illustrate a constant rate of change in the first 0.4 days of RV of 0, or about 28 meters cubed per day. Where's Brandon Bills? Did you do that? And what would that be like? Can you explain to me what that'd be like? He wants a horizontal line. Exactly. A horizontal line equal to what? RV of 0, or approximately 28. So what do? We used the rate value at the left side of the interval and made it a constant rate for the whole interval. I'll say it again. We used the rate of change at the left side of the interval and made it constant for the whole interval. I want you to do that for all 5 of these intervals. All 5 of these intervals. Okay, you ready? You should have drawn this. Ready? Watch. Here it comes. Does your graph look like that? It should. Okay? It should. Why are we doing this? Why? Because we like constant rate of change. We know the math really well. We are all experts at the math of constant rate of change. Okay? So we want to give ourselves constant rate of change to work with. See that? Because this is a continually changing rate graph. We're lost unless we have constant rates. So we're going to take these intervals and we're going to change them into constant rates because we are experts at the math of constant rate. Change in y equals m times the change in x. And final value of y equals initial value of y plus the change in y, which gets us accumulation from rate. Okay? So now, we're going to call this function just r. So we had r sub v. This function, we just made a new function. We just made a new function out of constant rates, and we're going to call it r. All right, and this r, it's a new function created from r sub v. What? It approximates the function r sub v. So the blue one, the horizontal bars, we just made a new function. We used the original rate function to do it, and now this new function approximates the one we started with. So we're going to call this the approximate rate function. Anybody who's had calculus before? Are you imagining rectangles right now?
Yes.
Wipe it from your brain.
But why do the sums are so cool?
Wipe rectangles from your brain. This is a new function. What happens with a function? For every value of x, one value of y. No vertical lines, no rectangles. Just erase it. Erase it from your brain. This is what we're doing. Okay, so let's practice this RV. So now for this new function, I want you to write each value exactly and approximately. What is r of 0.5, r of 0.2, r of 0.9, and r of 0.11, r of 1.1. So exactly and approximate. So an exact representation and an approximate value for each of these. So now this is a new function, right? Just the r, okay? Okay, so how would you represent exactly what r of 0.5 is? Exactly what r of 0.5 is. Where's Theodore Obert? Did you get that? 0.5 comma r 0.5. Where's Hannah Everman? Hannah, do you agree with that? You do. Okay. All right. So it's not a correspondence point. It's just a what? It's just a value of dependence. So it's a single value. How do we represent it exactly? She wants RV of 0.4. What do you think? That's correct. R sub V of 0.4. That's what R of 0.5 is. Right? Because in that interval from 0.4 to 0.8, all the values of the rate of change are RV of 0.4, right? It's that horizontal line that we got from at x equals 0.4. Yeah. I wrote the wrong thing. I was talking beautifully and wrote the wrong thing. Thank you. Does it make sense? Do you see that? So let's track it, right? Here, watch. So here's 0.5. We go up, and we want the y value of the new function r. What's the y value of the new function r? It's this y value, which we got from at 0.4, rv of 0.4. Okay, you want to try the other three again? So keep working on the other three. Take another minute. Oh, and so then approximately what? What is it? R 0.5 approximately? 17. Approximately 17. Where's Edgar? Chaldes. Did you get that next one? R of 0.2? He wants r sub v of 0. Agree? Where did all the rate values for that first interval come from? The rate at 0. For the r function, all those rate values in that first interval are rv of 0. So r of 0.2 is rv of 0, and that's approximately 28. So you get the picture here. Okay, r of 0.9. Where's Dominique Festa? R sub v of 0.8. And what about r of 1.1? Did you get that to that one yet, Dominique? It's the same thing, right? Because those two x values are in the same interval where the rate stays constant at rv of 0.8. Is this making sense? So what? So this new function is created from rv. It approximates rv with constant rates. Is this doing a good job approximating rv? Aiden says no. Why not? Okay. Yeah, so in those large intervals, it's getting, so like up here, it's trying to approximate this down here, doing a bad job. Do you see that? So for these like around values around 0.3, 0.4, it's calling the rate this when the rate is really this. So this is not doing a good job, but it's something, right? It's something we can work with because it has constant rates. Is there a question? Okay, yeah, so here, yeah, good. So down here at around 1.3, 1.4, 1.5, what? The rate of change is pretty close to constant, so then our approximate is mimicking that really well. Okay, so yeah, so for this interval, that particular constant rate does a good job, but everywhere else it's not very good. Okay, so now we got the feel for R. So now we want to write it as a. So can we write that function now? Right? It's made up of pieces, so we're going to need one piece at a time. Before we do that, though, I need to make a qualification. What we're going to do is for each of these intervals, we are not going to include, this seems counterintuitive, but this is what we're going to do. We're not going to include open circle at the left side, although that's the rate we're using. We're using the rate from the left side, but we're not going to start using it until just past the left side. And then we're going to go all the way to actually the left side of the next interval. So we're going to include that. And we'll see why we need to do that later. Okay? For now, just take my word for it. It seems counterintuitive. But this rate function is going to actually we're going to start the rate just to the left of the left side, just to the right of the left side of the interval using that value. And we're going to take it all the way to the right side of the interval, which is the same as the left side of the next interval. So do my circles filled in and open circles make sense? So it's kind of counterintuitive because we're using those left sides to get these rates, but then actually we don't want to use it in that interval. We want to still use the rate from the previous interval just at that breakpoint. So just take my word for it. So now we want to write this function. So we write it in pieces. So can you write this function r of x in terms of r sub v so that it gives you all values of r from 0 to 2? Okay? Have we done piecewise functions in this class yet? We haven't done it in the class. So what we're going to do is we're going to specify that first interval. Say 0 is less than x is less than or equal to 0.4. And so for that interval, what do we want r of x to be? What is r of x going to equal when x is in this part of the domain? He wants r sub v of 0. Yeah. So rx equals r sub v of 0. That's a constant value, right? That's just a single value for all these x values from 0 to 0.4. And then if we move on to the next interval, we don't want it at 0.4. We want to start just to the right of 0.4 and go to 0.8. Now when x takes on those values, what do we want r of x to be? Etc. So can you finish it? So you're going to have 5 lines. Okay? You're going to have 5 lines in this rate function to get from 0 to 2. To get from 0 to 2 days, you're going to have 5 lines. So you finish. Jacob, I'll take that as a hand. All right. Big stretch. Okay, so from 0.4 to 0.8, what is our rate function? And want to do the next line too? Okay. Yeah, and how's he doing? Making sense? Okay, so I'll just write out the rest for time's sake. So we're going to have r sub v of 1.2, and that'll be from 1.2 to including 1.6, including the right side, and then finally okay, questions on that? So that gives us, so this now defines that rate function. Every single correspondence point on our blue step function, our blue horizontal constant rates. That defines every single point. So we have to know what our x is first. And once we know what our x is, we come into the line where that x fits in, and then it tells us what that rate is for that x value. Okay, so now what we want to do is we want to use these rates to sketch if that was indeed the rate function, the constant rates. We'll often call a step. Remain calm.
That's 2 fire drills this morning.
Okay. All right. Should I leave it on the video?
Yeah.
Of course. All right. Okay. So we want to now, can we get, all right, can we, okay. So let's, according to that new rate function that we have, just plain R, can we sketch what the accumulation of oil would be? What's our accumulation of oil at 0? How much oil do we have at 0? 0, right? We said that. So last time we didn't say today, but okay, so at 0 we have 0. Okay, and so if 0.4 days go by at our approximate rate of 28, or yeah, 0.4 days go by at our approximate rate of 28, what accumulation of oil will we have after 0.4 days? How would you find that? What would you do? What I'm asking for a change in V. And changes in V equal M dx. So what's our rate, constant rate? We're approximating 28, right? So this is approximately 28 for, what's our dx? 0.4. What's 28 times 0.4? Tell me. Nice and loud. 11.2? Beautiful. 11.2. Here it is. See that? And what's the graph going to look like in between? If, why straight line? Yeah, so we're assuming this constant rate of 28. So to get from that point to that point, it's going to be constant rate. Let's see if I can do it. Terrible. A little higher. That's better. That's supposed to be straight. Not bad. Okay. Now, so we did what? We did dV was 28 times dx, which is 0.4. Okay? So now, that's dV1. So now, how much is it going to change in the second? In the second interval, how much is our, tell me. 17 times 0.4. And what's that? 6.8? So now I'm going to go here to 0.8, and I'm going to do 6.8. No, because we want V final is V initial plus change. So what is our change in the, so our change from the new rate of change is 6.8, is that what I heard correctly? Plus what we had to start with, which was our 11 point. So what's the new value of exactly 18? At 0.8. 18, it's just over this line right here. And throughout that whole interval, we assumed a constant rate of 17, so straight line. So this is the correspondence point, 0.4, comma, 11.2. And then the next one is 0.8, and final value of V equals initial, our 11.2, plus the change we got from M dx, which was 18. Is that right? Okay, so we could easily finish in this way. So we could get the change from each interval, add it to the current accumulated amount from all the previous intervals. That would be our V initial in each interval. Would be the accumulated amount from previous, add the new change, and we could find these ordered pairs. And then, for each interval, then we could say for any x, right? So any x, what is Vx? And then in this interval, so now I've got for any, so call that x1. For any x2 in that interval, what would Vx equal? We've done it before. We've done it a lot. And so for each interval, we could just assume a arbitrary point in that interval and find the final value of accumulation for that arbitrary point. And now what we're doing is we're creating that function. We're actually getting what every value of accumulation would be for every x value. We have to do it a piece at a time, though. An arbitrary x in the first, an arbitrary x in the second piece, an arbitrary x in the third, so that this function called capital A, which you can't see there, capital A would be like this one, would be a piecewise function, and would give us this accumulated amount at any value x. So that will be So this is going to be, I'll clarify that. This will be additional written homework for Wednesday in addition to what I signed over the weekend. Make sure you look for that on Blackboard.